today is to look at the graphs of some rather unusual functions and in some cases relations. So let's look at a number of examples. Here we have a function defined in a rather special way in which its f of x is equal to 1 if x is greater than 0, f of x is equal to 0 if x itself is equal to 0, and f of x is equal to negative 1 if x is less than 0. So let's then make its graph and see what it looks like. Now, let's then take the first case, or the top case here. F of x is equal to 1 if x is greater than 0. Would look like what? How may we make its graph? And Brenda?
An open circle on one and the y-axis or the f of x-axis.
All right.
And then a solid line to the left.
And a solid line to the right. And that line then goes on forever. Is that right? So we may indicate that by this part of the graph. And now f of x is equal to 0 is then going to be what, Glenn?
A solid point on 0, 0.
A solid point right at the origin. Good. And now f of x is equal to negative 1 if x is less than 0. What then can we say about that, Bill?
An open circle at negative 1 on the f of x-axis and a ray to the left.
And a ray to the left, indicating that this will then go on forever in this fashion. Very good. Now again, this looks like a rather unusual function. It's given a special name, and it is called the sine function, S-I-G-N, the sine function. And some people refer to it as the signum function also. Now, in fact, it turns out to be quite an important function, for example, when one is using a computer, because there are many examples, many situations which require knowing something like this. Well, let's look at another rather unusual function. Here we have a notational device of y is equal to with these heavy brackets around the number x. And this function is given a special name, and it is called the greatest integer function. And we have to define what we mean by this greatest integer function. And what we mean is that integer and the greatest integer which is less than or equal to x. All right, for example, suppose we have here x is 1.5. I want that greatest integer which is less than or equal to 1.5, and of course it's going to be equal to, Brenda?
1.
It's equal to 1. So the greatest integer of 1.5 then you say is equal to 1. What's the greatest integer of negative 4 equal to? And this then, Dick?
Negative 4.
Negative 4. What then is the greatest integer of negative 4.3? And this then is going to be equal to, Doug?
Negative 5.
Negative 5. Does everybody appreciate that? Okay. So let's then see if we can't make the graph of this function. And if x, say, were 0, the greatest integer of 0 is 0. Is that right? Now, if x, say, were a half, the greatest integer of a half is 0. But the greatest integer of 1 is 1. So, in fact, the graph has to jump up to this point. So between 0 and 1, it's going to be a heavy line and then an open circle. Is that right? And now, the greatest integer of 1.5, for example, is 1, so I think you'll agree that it's going to be along there and then an open circle, and then it's going to include this point and then an open circle, is that right? And then this point and an open circle, and I think we then can see how this is going, and in fact it's going to go on forever in that fashion. And now let's look then for values on the negative side. For example, if x were negative a half, what's the greatest integer of negative a half? Negative 1, is that right? And in fact, what's the greatest integer of negative 1? Negative 1. So this point then is on the graph, and a heavy line, and then an open circle right here. And I think then you would agree that if this point's on the graph, and an open circle, this point and an open circle, this point and an open circle, and so on down in this fashion. And notice there, it looks like a set of steps. And in fact, this is also popularly called a step function. Well, let's look at another variation of this one, and here we have y then is equal to the opposite of the greatest integer of x. And what then is the effect of that dash symbol on the graph? What then do you think that it does? Perhaps one description would satisfy this, and does anybody have anything in mind? Any time off. For example, if x, say, were 2, instead of having a value for y at 2, it then would have to be the opposite of that number. Is that right? So therefore, what is the effect on the graph? What do you think is going to happen? Tim?
It'll be a diagonal line that way.
A diagonal line this way?
No, the other way.
The other way.
Yeah.
Rather than a diagonal line, it's then going to consist of, what, steps. Is that right? The steps now are going to come from left to right in a downward fashion. Does everyone agree with that? In other words, is this point still on the graph?
Yeah.
And then at 1, we're then going to jump down here to a negative 1, is that right? So our steps indeed are going to go down, and so on forever in this fashion. Perhaps our coordinate axes are quite small here, but I think you can see that indeed it's going to look something like this. Is that right? Everybody agree with that? Okay. And again, as I say, I think that this is a rather unusual looking graph, and we have our steps coming down. Well, let's look at a fourth example, and here we have a function y is equal to the absolute value of x over x. And again, let's think about this. Of course, there's one number which cannot be in our domain of x, and what then would that number be? John?
0.
X cannot be equal to 0, because 0 is division by 0 here is undefined. Of course, if x were greater than 0, the absolute value of x by definition is x itself, and so we have simply x over x. So what then is our graph going to look like? Doug?
1.
It's going to be at
It would be a horizontal line.
a horizontal line passing
Y-axis,
through
passing through 1.
And right here at 0, it's going to have what? An open circle, and then a ray. Is that right? Let me use that word, ray, going on forever in this fashion. And in fact, when x then is a negative number, the absolute value of a negative 3, for example, is equal to what number? It's still 3, but then in the denominator, we have then the number negative 3, so 3 divided by negative 3 is negative 1. So what then is the graph going to look like when x is negative? And Kirby?
Let me think. An open circle at negative 1 on the
An open
y-axis.
circle at negative 1 on the y-axis. Good.
And a line to the left.
And a line to the left. Does everyone agree with that? Okay. The line then would come to the left, and in fact, let's call that a ray because it goes on forever in that direction. And let's look at this one. It's almost the same as our sine function in number 1, except the sine function also has what point on it? We have defined it in 3 different ways, so it includes the origin. Is that right? Whereas here in our example number 4, we don't give this function any special name. There is no value when x is 0. Okay? Let's look then at another example. Here we have y is equal to the absolute value of x minus 2. Now, if the negative 2 number were not there, we know what y equals the absolute value of x looks like, what its graph looks like, and I think you all will agree that it's going to come out in this fashion. We've done that one before. What then is the effect of this number 2 there, this minus 2? What are we going to do there, Brenda?
We're going to move it down on the y-axis 2 points.
We'll move it down from the origin. The point, or the corner point, so to speak, will then come down 2 units, and indeed this then is going to be our corner point. Does everyone agree with that? So let's then, if we were to run 2 units, we then would have to, what? Rise, what? 2 units. And I think this point then would be on the graph. If we were to run to the left 2 units, we then are still going to do what? We're going to rise 2 units, and this point is going to be on our graph. So let's indicate that by this line, this ray with the endpoint included, and also this ray with its endpoint included, and I think then you'd agree that this is its graph. Well, let's do some variations of the absolute value function. And looking at example 6, here we have y is equal to 1/2 times the absolute value of x minus 1 plus 1. Now, let's take it one step at a time. If the number 1/2 were not there, and if the number 1 were not there, we would simply have the absolute value of x minus 1. Now, let's look at that and ask ourselves, where would the corner point be if that were simply the function that we were concerned with? And what then, where would the corner point be? For what value of x would make the absolute value of x minus 1 equal to 0, would be the question. Don?
The coordinate 0 minus 1.
At 0 comma negative 1. Well, in the example that we had here, in example 5, the negative 2 was outside the absolute value, and that had a tendency to pull it down, or else push it up, depending upon whether it were negative or positive. But here we have this number inside the absolute values, the absolute value of x minus 1. So for what number x then is this then going to be equal to 0? And Brenda?
1.
When x is 1, y will be 0. Ignore the 1/2, please, and the number 1. Is that right? So when x is 1, y then would be equal to 0. Now, let's take into consideration this number plus 1. Again, still ignore the number 1/2. Now, if we then were to add 1 to this point, instead of our corner point being here, we're going to do what, Charles?
It would rise 1.
It would rise 1. All right, so I think our corner point is going to be right here at this point here. Would you agree with that? Now, let's think about this number 1/2. Well, again, if the 1/2 were not there, what then do you think the graph would look like? If we were to, say, run 2 units, we would have to rise how many units? 2 units if the 1/2 were not there. The fact that the 1/2 is there, what then do you think you're going to do? Doug?
If you went over 2, you have to rise only 1.
All right, if we were to run 2 units, we would rise only 1 unit. Is that right? Everyone agree with that? All right. Now, from this point then, if we were to run to the left 2 units, how many units are we going to rise? We're going to rise simply 1 unit. Okay? Now, again, let's think in terms of if the absolute value symbols were not there, we would then have 1/2 of x minus 1. Isn't that right? And we may think in terms of for values of x which are greater than 1, you would then think in terms of a slope number of what number? The slope number would then be 1/2. And I think you would agree then that a slope number of 1/2 would be such that we would run 2 and rise 1. Is that right? And I think once we have those 2 points on our graph, we then can make our half line, including the end point in this direction, and the half line and the end point in this direction. And notice with respect to our absolute value of x function, what the number 1/2 has a tendency to do is to widen it, so to speak. Is that right? To spread it out a bit. Well, let's look then at another example. Here we have y is equal to the opposite of the absolute value of 2x plus 4 plus 3. And looking at that, you say to yourself, well, I think I may factor out of the absolute value symbols the number 2. Is that right? So let's just then take that number 2 out, and we have plus 3. Now, if the 2 were not there, but the opposite were there, and let's then also forget about the number 3 for a minute. All right. In fact, let's also forget about the number or the dash symbol for a minute and look at simply y then is equal to the absolute value of x plus 2. Now, where then is that corner point? Where do you think the corner point would be if we were simply looking at the absolute value of x plus 2? Peter?
Negative 2, 0.
At negative 2 comma 0. Does everybody agree with that? When x is equal to negative 2, y then would be equal to 0. Okay? Now, let's still ignore the number negative 1/2, or negative 2 rather, and now let's add 3 to it. And what then is the effect of adding 3 to that graph?
Rise.
It will rise 3, all right? So Peter then says that negative 2 comma 1, 2, 3 is going to be our corner point. Now, is our graph going to open upward, or because of this dash 2, this negative 2, is the dash symbol, that opposite symbol, going to do what to the graph? Kirby?
Make it open down.
It's going to make it open downward. And if the 2 were not there, I think then you would agree that it would come out like this. But now, what is the effect of having that factor of 2 there, Doug?
It makes the 2 lines closer together.
It makes the 2 lines closer together. Good. For example, if we were, say, to run 1 unit to the right, how many units are we going to fall?
2.
We're going to fall 2 units. Does everyone agree with that? So this point then must be on the graph. And of course, if we were to run 1 unit to the left, how many units are we going to fall? 2 units. And this point then must be on the graph. And if we then were to make our half lines, including the end points, in this pattern, it then is going to look like this. And coming down on this side, it's going to look like this. And our graph is going to be more narrow than the graph of simply the absolute value of x. And I think it's going to look like this. Now notice, rather than looking at our original formula here and picking out ordered pairs and trying to plot them on our coordinate axes and then put in a lot of points on there and then put in the lines, we are looking for a pattern. And if you start out from a basic idea and just continue to build onto it, you can come up with these graphs rather quickly. Okay? Well, let's look then at a last example. Here we have the absolute value of x plus the absolute value of y is less than or equal to 4. And let's see what we may say about that. For example, if x, let's think in terms of the equality part first, all right? the associated equation that has to do with simply is equal to. Now, if x, say, were equal to 4, 1, 2, 3, 4, what would y have to be in order to make the sentence true? 0. So I think you would agree 1, 2, 3. This point would have to be on our graph. Now, if x were equal to 0, what number can y be?
4 and negative.
4 and negative 4. 1, 2, 3, 4, and negative 4. 1, 2, 3, 4, these 2 points. And in fact, if y were 0, x can be 4 and also negative 4. 1, 2, 3, 4. Now we have those 4 points on our graph. And does anyone have any idea what the graph might look like? Bill?
It's going to be a square with those 4 points as the corners.
Good. It's going to be a square with these 4 points as the corners. Let's indicate that. The square is sort of on this edge in this fashion with respect to our coordinate axes. All right, let's include those points, and now then we want those points which are less than or equal to. And Bill?
It's going to include the region that's inside of that square.
Inside of those points. And let's shade that region in this fashion. And our graph then will consist of all points which are on these lines and inside of this square, so to speak. Is that right? Well, I think that that's all that we need to do for today. So let me give you your homework assignment. This will be a